Okay, I think we can start now with the webinar. I welcome everybody to this webinar about orthogonal layouts. My name is Benjamin Niedermann. I'm a software developer at yWorks and a member of the layout algorithms team. So this basically means that I daily work on layout algorithms, improving them, implementing new features, but I also develop new layout or visualization techniques that you can use to visualize your connected data. And apart from that, I also give this series of webinars on layouts where I would like to introduce you to different types of layouts that are offered by yFiles. So yFiles is the main product of yWorks, a library that you can use to visualize your connected data. And one part are these many layout algorithms that you can use to visualize your data. And today I would like to take a view on a very special layout type, namely orthogonal layouts. And I would like to answer the questions how to use them and when to use them. But before that, I would like to first clarify what do I mean actually with orthogonal layouts. And with orthogonal layouts, basically the figure on the left-hand side already tells you this. With orthogonal layouts, I mean graph layouts where the edges are drawn such that they only consist of horizontal and vertical segments. And this assumption, of course, influences the positions and the placement of the nodes significantly, and also the shapes of the edges. So if we decide, for example, that an edge should not have any bands, then we can only place the nodes either on a horizontal line together or on a vertical line, like here. Or if we allow bands, so for example like here, then we can actually place the nodes a bit differently, but in that case we of course need to reroute the edges. And this is a very typical problem then for orthogonal layouts, to find a good layout where we only have few bands so that the visual complexity is low. And after saying this, I now would like to show you when to use orthogonal layouts, and for that I would like to present some use cases. A very typical use case are, for example, UML diagrams. So basically, in more generally said, technical drawings or technical diagrams, and especially UML diagrams. On the left-hand side, you can see a typical class diagram where we model some classes with some attributes and some operations, and then we have some connections, and these connections are drawn orthogonally. And on the left-hand side, you can see a screenshot of an example that you can also find in the yFiles demos. So here we just use the standard UML style offered by yFiles. On the right-hand side, you can actually see how it looks in a real application, namely in the IDE of JetBrains, where they use class diagrams to represent or to show the structure of actual code. And JetBrains is one of our customers that who use class diagrams or our product to draw class diagrams. Then another use case are decision diagrams. So again, some typical UML diagram also, where it's about drawing or displaying possible decisions, where we have, for example, different start nodes and some lanes structuring our graph, and then we would like to model these decision diagrams. And in order to have a very clear representation of the edges, here again we use orthogonal edges. So the edges only consist of vertical and horizontal segments, and of course we can round up these corners in order to make it a bit more smooth. And this is again an example from the yFiles demos, and here I also would like to show you an example from a real application, namely from Apollo Systems, that basically also use yFiles for this. They have integrated this layout into a more complex visualization system that shows or that is used for process monitoring. And here again, they have some kind of decision diagram where they use an orthogonal layout. As a last example, I also would like to point out tree diagrams. So here the idea is that you, for example, have a hierarchy that you would like to represent as a graph drawing, and this you can of course do with tree diagrams or tree layouts. For this I also refer to the webinar that I have given in the last year about tree layouts if you want to know more about this. But again, here you can use orthogonal edges to draw this diagram. And on the right hand side, so on the left hand side, this is again an example from the yFiles demos, and on the right hand side you can see how it is used in practice. Here it's about displaying the network of switches, for example, and then you have these typical tree structures here with these many leaf nodes that are also aligned on the same line, and this gives you a very structured view on the graph. And so now I have shown you some example how you can use actually orthogonal layouts, and you obviously can do this with yFiles, but the question is, of course, how can you do this? And there are many, or there's different possibilities how to do this or how to achieve this with the yFiles. So one possibility is that you take an existing layout and you keep the nodes fixed and you just reroute the edges. So here what I've done is I just layouted this graph with the organic layout, which only supports straight line edges. And then you use an extra algorithm as a post-processing step that then layouts the edges using the orthogonal principle. And here what you can see is that many of these edges are routed around the graph nodes, because otherwise if you would use the direct ways to the nodes, you would get many crossings, which would increase the visual complexity. So here you can see another challenge when creating orthogonal layouts. It's not only about reducing the number of bands, but a contradicting optimization criterion is the number of crossings. So this is a typical problem that you get when you want to create orthogonal layouts. It's a balance, the question between the balance of bands and crossings. And in March, so in about 8 weeks, I will give an entire webinar on how to configure edge routers of yFiles, and also how to do this for the orthogonal layout. Another possibility to obtain orthogonal layouts is just to use specialized layout algorithms. So there's, for example, the hierarchical layout and the tree layout. Both I've already presented in other webinars that you also can find on YouTube. And then there's also the special layout, which is called orthogonal layout, because this layout algorithm is really dedicated for orthogonal layout. So this is a layout algorithm that only can produce orthogonal layouts. And in this webinar today, I would like to present this special layout algorithm. And to that end, I want to structure the webinar in 3 parts. Namely, first I present some principles on this orthogonal layout algorithms that are important to know when using it. And then after that, I show a demo that you also can access using your web browser. And then in the final step, I would like to also give a short coding example showing you how to do some basic configuration for a simple example. And at this point, I would like to point out that if you have some questions, then please just use the chat, and I will try to answer the questions after this webinar. In case that you are watching this video after this webinar has taken place, then just leave some comments in the YouTube below the YouTube video, and we will try to answer them as soon as possible. So let's start with the orthogonal layout. And the first thing that I would like to explain are the principles. So first of all, I would like to mention that the nodes are placed on a grid. So this is also a difference to the other layouter. So for example, the hierarchic layouter does this on layers. It can be configured that it also places the nodes on grids, but this orthogonal layout algorithm that I now present has this basic assumption that the nodes and the bands are placed on the grid. And with this, we also get some restrictions. And what we also want to do is not only to minimize the number of bands and the number of crossings, but we would like also to reduce the grid size that is actually used so that we get a compact layout. And another assumption that we do is that we use the so-called Kandinsky model. So when orthogonal layouts were introduced first in science, the assumption was that each node can only have 4 incident edges, so for each side 1 edge. And this is of course very restrictive, especially in applications. You normally have graphs with higher degree nodes. And the solution was then to introduce the Kandinsky model, which basically says that a node can have an arbitrary number of incident edges, but if 2 or multiple edges leave the same side of the node, then there's a center edge that does not need to bend, but all other edges bend. So for example, this on the left-hand side bends to the left side. And for the edges on the right-hand side, they bend to the right. And this is an assumption that is made by this orthogonal layout and should also explain you sometimes when you see this layout why they have been created in such a way. So this is basically an information for you to understand why the layouts look how they look like. In the next step, I would like to shortly sketch the approach, how this is done. This is a very high-level view, and this should give you some idea how the criteria are optimized and how to apply this layout. But you don't need to take care about this too much, and also not about the details. This is basically what we do here when improving this algorithm. So the idea is that we are given an input graph, a completely arbitrary input graph, and the first thing that we do is that we fix the topology. This basically means that we put the nodes into the plane, and we already roughly decide how they lie relatively to each other. So basically what we do is we decide the order of the edges, how they come out of the nodes, and this gives us already a rough drawing, and this gives us the information where the crossings are. So, and this helps us, or what we then do is that we try to optimize the number of crossings in this step. So we put a lot of effort into this algorithm such that so that the number of crossings is minimized. And these crossings are then replaced by dummy nodes. So basically then we get a graph that has no crossings anymore. And important also to know is that if you input a graph that can be drawn without any crossings, then this algorithm actually leads to a graph drawing that also has no crossings. Only if it's not possible to draw your graph without crossings, then we minimize the number of crossings. The next step is that we do the so-called shape step. And here the idea is that we define the shape of the edges, which basically means that for each edge we decide where the bends are and which segments are horizontal and vertical. So for example here this node A to D, or this edge that goes from A to D, for this we say okay, the first segment should be horizontal, then there's a right band, and then the next segment is vertical, and then the next segment is horizontal again. And this we do for every edge, but at this point we don't know anything about the length of the edges. And again, we don't do this arbitrarily, but we minimize the number of bends in this step, so that the drawing has only few bends if possible. And then in the final step, we assign the length to the edge segments, and this basically means that we define which nodes lie on which grid points and how far away these grid points are. Actually, you can also configure them later on so that you can say, okay, that you would like to have a certain grid spacing. But here at this point, we say, for example, that these two nodes here, E and C, are 1 unit apart from each other, whatever 1 unit means in this context. And again, we don't do this arbitrarily, but similar to the previous steps, we do this in an optimized way. So what we do is we minimize the width and the height of the drawing so that the drawing becomes compact. So summarizing the approach, what we get is an approach that optimizes the layouts in 3 steps. Namely, it optimizes the crossings, which is the first priority. Then it optimizes the bands. And then lastly, it optimizes the compactness. And in total, you get an algorithm that gives you an orthogonal drawing. When this was developed first, so this is an approach that has been known in science for a long time, but only for very for graphs without many features, and we invested a lot of effort into this layout algorithms to also support further features that are typically important for the practical use. And so, for example, here are 3 typical features that are supported by the yFiles algorithm. So on the left-hand side, you see a typical class diagram, and in this class diagram, you have these hierarchies between the classes. So this some inheritance edges here, and then you have some associations. And for the inheritance edges, you would like to normally have directed edges so that the parent class is at the top and then the child classes are below this. And this can be done with the yFiles algorithms. Then another important feature are groups. So you can also group the nodes and introduce group nodes. And then finally, there are also the substructure feature that you can use to express or to represent certain structures in the graph with a specialized layout, so that you really know how this layout will look like. So for example, this chain here, for that you can define that it should be wrapped and should not be just a long line. And these are 3 example features. So the orthogonal layout has many more features, and I won't go through all of them, but I at least want to show you in this webinar how to use the directed edges and also the substructures. And to that end, I want to go to the next part of the webinar, namely to the demo part. Here in this demo part, I would like to present a demo that you actually can also access on yourself. So for example, after the webinar, I recommend you just to use and to play around with this demo and also with the other demos, and there you can easily find out what the layout algorithms actually can do. So I open this demo, and we have here this graph. It's an orthogonal layout already, and I just have used the basic configuration for this graph. And here's this panel that you can use to configure your graph. And this is of course only a demo, and everything that I do here on this right hand side on this panel you also can do, for example, in a programmatic way using the API. And typically there's a direct mapping from these properties to the API, so often it pays off to first play around a bit with the layout algorithms in the demos to find out how they work, what kind of features they have, and then to see how to use this on your own examples. And yeah, here are some typical general properties that you can set. So some Boolean flags, it's about whether you want to reuse the drawing that you already have and want to derive an orthogonal drawing that is similar to the input drawing, but there are also many other properties. So I don't want to go through these, but I would like to focus on the substructure layout feature. And here the idea is that you can recognize or detect different types of substructures and tell the layout algorithms to specifically lay out these structures in a different way. Let's have a look at this chain here, for example. This is just layouted in a very long line, reducing the number of bands, of course. But often you don't want to have these chains in a long line, but you would like to wrap them up. And for that, you can use this special feature here. You can go here to this option, and this says wrapped with nodes at turns. And if I apply the layout again, what happens is that the chain is wrapped here, becoming much more compact. There's also this option that the bands that at turns there should be bands. So here is a turn, and here we have placed a node here also. And if I choose this option, what we get is that at the turns of this chain, there are bands but not nodes. This is sometimes nice to have for certain types of layout styles. The same you can of course do for cycles here. You can choose that the cycle should be detected and specifically layouted within certain layout style. And now the nodes lie here on a circle, basically in rectangle in the orthogonal case, of course. And finally, here I would like to show you how to do this with a tree style. There's, for example, this integrated tree style. Here the tree is then layouted in between the other nodes and the edges go around of this. There's also a compact style where you can place the tree such that the tree is layouted really compact, so it really takes only few not much space. And this already should give you some ideas what you can do with this layouting or with the orthogonal layout algorithm. And if you would like to see more, you can use here other types of properties. But I now want to go back to the slides and go to the next part, namely where it's about how to use this layout algorithm actually in the coding example. And the idea of the coding example is that we are given an UML class diagram here, and this is obviously not layouted yet. And it's not important to know what the classes are about. It's about a simple drawing editor. So I've created this class diagram a few days ago. And the idea is that at the end we would like to get an orthogonal layout where we have certain properties. So for example, here we have an inheritance structure of the classes, and this should be layouted such that it's in a tree style, style. And also the distances between the nodes should be appropriate, and yeah, there are many different things that you can optimize in this layout, and this should be then the result. And to show you this coding example, so this coding example will be in yFiles HTML. I will use TypeScript to do this, but if you come more from the Java side or the .NET platform, you basically can do the very same as the API is basically also the same. So at first I would like to introduce the basic setups and some basic features. To that end, I go to this coding example, and this is basically the output of our algorithms, and I only will edit here this method. It's called runLayoutCore, and every time I refresh this tab here, so this demo here, this method is called, and I can then do the layout on the graph on the given. And to that end, I first create an orthogonal layout. And I apply this layout on the graph. And when refreshing this, I already get some layout, an orthogonal layout for this graph. And what I also can do is that I can specify certain properties. An example that I would like to show you is the align degree 1 nodes. And if you have a look at this node here, for example, and this is a typical thing that can happen with the basic implementation, is that these degree 1 nodes are not aligned with the other nodes. And what I would like to do at the beginning is just to move this. And I just want to show you how to set simple features, so that the reason why I've chosen this feature here. So when I've done this, I can refresh this. And then what you can see here is that this node is aligned with the other nodes. Another important property that often pays off to use is the phase maximization property. So what does this mean? If I set this to true, what happens is that the outer phase is maximized. So what is a phase of a graph? So if you look at this drawing here, these edges subdivide the plane into different regions, and so for example into this region here, and this is called a phase. And you have a lot of these small phases, and you have one outer phase, namely here this infinitively large phase in the outside. And what this property does is, in the first step of the algorithm, so when we fix the topology, it takes the phase as the outer phase that is maximized. So, and this typically leads to a drawing where the nodes in the interior are more compact. So I just refresh this, and what happens is that you get here a bit more compact layout. Here, for of course, this tree structure is still outside, but it's a very special type of structure. It has no cycles, and it's placed outside there. For this, we take another approach later on to visualize this in a better way. But so basically, what you've seen in this very short part of the coding example is how to basically set up this. And there are many different properties that you can also set here. The next thing is, so this is basically the result that we get with this. And the next thing that I would like to consider are distances. So if you have a look at this part here, the edges are very short. And there are different possibilities to influence the distances, and this is often one thing that you also need to do to get a good balance between the node sizes and the length of the edges. And there are two possibilities in general how you can change the distances. Either you change the grid spacing, so as I said, the nodes lie on grids, or on grid points, and what you can say is that you want to increase the distance between two grid points. This influences, of course, the overall layout. And then what you also can do with the orthogonal layout, you can say that the how long the first and last segment should be at least, and how long segments in general should be at least. And this is what I would like to show you next. So for this, I can use the property grid spacing, and this just says how large the distance should be. I just input some great number at this point so that you can see the effect of this. Later on we'll use a more appropriate value. But if I put here, for example, 200, you basically see what happens is that we have here a distance, a really large distance between the nodes, and also in the vertical and in the horizontal direction. So this gives you an overall possibility to influence the distances in your layout. So I set this back to, let's say 50, because this is much more reasonable for this type of diagram. And sometimes I need to refresh here. No, and that's better. And as an alternative, I can define the edge layout descriptor, and here the minimum first segment length, for example. So if you have, if you consider an edge, it consists of multiple segments, and going along this edge, there's a first segment and last segment, and here you can define the minimum length of the first segment. So I set this, for example, to 80, and what you get is that actually the length here becomes a bit longer, and it looks a bit more reasonable or better in the sense that they are not too packed, the nodes. Of course, I can also do this with the last segment, but as most of the edges are straight lines here, okay, or are already very long, this will have not that much effect on this layout. So this is a very simple possibility to already do a basic setup of your layout. The next thing that I would like to show is how to do substructures. So if you consider here this tree, as I said, this is an inheritance tree, so of classes, and of course at the moment it does not look like a tree, but what we especially not like an inheritance tree where we have this kind of layering, and this is the next step that I want to do. And with this step I also want to do the direction of the edges, so I will aggregate or do the third and fourth step in once. For the fourth step I will I go back to the coding example, and then you will see how I will do the fourth step, where it's about directing the edges of the nodes. So for the third step, this is really simple. We just have this property tree style, and we say this tree style should be integrated. And if I refresh this, what now happens is that the layout algorithms tries to detects trees in the layout, and then these trees are specially layouted. And in the demo that I've shown you before, this is basically this property that I have chosen using this drop-down menu that also said integrated style. And yeah, it's basically setting one property. But what you can see here is the problem, or typically you want to draw trees not, especially inheritance trees, not from bottom to top, but from top to bottom. And to that end, I want to say how the direction should be. And the idea is that the layout has a layout orientation, and the layout orientation currently goes from top to bottom. And what I now specify is the edges that should comply with this layout orientation. So for this I need layout data. And I just also add this layout data to the apply method. And the layout data is a further possibility to configure your layout algorithm. And the layout data basically works on specific nodes. So here you can really say, okay, for specific edges or nodes, how they should behave in the layout. And what I do is that I say that the directions of the inheritance edges should comply with the layout. And to this I say directed edges. this should not be layout, but layout data. And here is the directed edges. And here you have different possibilities to define these directed edges. So for example, you could just hand over a collection of edges that should comply with the layout orientation, or you can specify them directly using mapping, or you can also use a delegate. In this case, I use a different way. I just define the predicate function that is used to decide whether an edge is an inheritance edge or not. And this method here, so this is inheritance edge is a method that I wrote before. It's a helper that just expects an edge and returns whether the edge is part of an inheritance tree or not. So it returns not for or false for example, for this edge here, but true for this edge. And I just use this as a predicate directly on the direct edges. If I refresh this, I get that the tree is now layouted, that the root node is at the top and all other nodes are below this top, and then we have this recursive definition where the next layer nodes lie below and so on. And the very same also happens for the other inheritance trees. And here I maybe also want to mention one thing. If I uncomment this, and this is the old drawing, but you will recognize that this, for example, is an inheritance tree, but this is not layouted as a tree, not in the same way as this tree, for example. And the reason is that the algorithm only detects this as a tree. So this is a tree with the root node here, and these nodes do not belong to this tree because of these two edges. But also defining this directed edges, we also get this property here that the nodes that are not the root nodes lie below the root nodes. And this also helps you to visualize these inheritance trees better. So this showed you how to use substructures. Using substructures is very simple. Just set a property, how these substructures should be detected and layouted. And then I also showed you how to define directions of the edges. Where it's about saying that the root node, for example, should lie at the top. And the idea was to just use the layout orientation to define edges that should comply with the layout orientation. And finally, of this coding example, I would like to go to the edge grouping. And what you can see here is that the inheritance edges of this class diagram are not grouped. So basically what I would like to have is a case like in this actual tree drawing here, where the edges lie on top of each other, so that it looks like that this is only one edge here. So this helps to reduce visual complexity. And this is also what I would like to do here. The reason is that this is also already done in this part of the drawing is that this is recognized as an entire tree, and for the tree layout this is done automatically. And here I need to do this, or I need to specify that I would like to do this. And to that end, I just go through all nodes and will define for each node which edges should be grouped. So I go here through the nodes. And I consider all outgoing edges. So I consider all these edges here. I need to consider the outgoing edges because in the UML style, this is an edge that is actually points from here to here. So this is basically an outgoing edge of this node here. So I consider all outgoing edges, of the node. This gives me these edges here, for example. And then I only want to have a look at the inheritance edges, but not at the association edges. So not at this edge, for example, but I only want to have these edges in the hand. So for that, I filter them. And this is basically a simple predicate. And here again, I use this is inheritance edge. Like this. So now I have these edges. And on these I apply or I define a grouping ID so that the layout algorithms know that we want to group these edges. So on for each, and then we say for these edges we would like to group them, and this can be done also using the layout data. And there's the source group IDs, and we specify for all these edges the same source group IDs. Oops. You can use any kind of ID here. So I use just a string and I call it group, but you can use anything that you would like to use here. And now the layout algorithms know that we want to group these edges here. And here it worked. Yeah, also I'm not sure what I've done here wrongly. Okay. I think the reason is that that's also fine that this happens. The thing is that here it's appears as a tree layout, and here it's so this is recognized as a tree, and these nodes are not recognized as a tree, and this is the reason why this is not put together, I assume, at least. I'm not sure at this moment, but I think so. I can also clarify this later on. But this basically shows you how to group these edges. So for example, here these two edges are grouped, and also these edges are grouped. And this specifier did this. And with this, I would like to go back to the slides, and this is then the result. Okay, also in this result I have this. So basically this explains it. This tree here is layouted differently than these nodes here, and this is the reason why these edges are not grouped at this point. And with this I would like to finish the coding example, and I would like to go to the conclusion part. And for the conclusion, I think what you should have learned in this webinar is that there are different approaches in the yFiles library how you can obtain orthogonal drawings. So there's this approach where you just take an existing layout and then you reroute the edges. And as I already said, there will be a webinar in March entirely about this topic, not only probably for orthogonal edges, but also for other types. And then, but mostly I think for orthogonal edges. And then there are also different ways or different layout algorithms that you can use that have an integrated edge routing for orthogonal edges, like the hierarchical layout, the tree layout, the series parallel, which I haven't mentioned before, and then the orthogonal layout that you've seen today in the webinar. And here the idea is that this is a grid-based approach that optimizes the layout in 3 steps, minimizing the crossings, minimizing the bands, but also the improving or optimizing the compactness. And with this, I would like to finish the presentation of the orthogonal layout and go to the question Q&A round. And now I would be happy to answer your questions. So I will have a short look to the chat, and then we will see. Okay, here's the question, which with orthogonal layout can we have it okay, it's basically about edge grouping, I think. The question is whether it's possible to merge edges and also to split edges. And the idea is, yes, you can do this with the orthogonal layout using the edge grouping, so that you can basically merge these edges, or after that you can also fork them. Yeah. I hope this answered the question. Then the next question is, in UML diagrams, edge labels often lie at the endpoints of the edges or at the center of the edges. Is it possible to do position the labels? And yeah, so about labeling I haven't said anything yet, and there is this possibility to place the labels, so to specify where the label should lie. For this you can use a placement descriptor that you can configure. So for example, saying that the label should lie at the beginning of the edge or the end of the edge, and also on which side of the edge and with, what kind of rotation. Yeah, and labeling is also an important part of layouting, and yeah, I hope that I once can do a webinar also on this topic. And the third question is, I would like to use partition grid and port constraints with orthogonal layouts. And the question is whether this is possible. And here I need to say, unfortunately, it's not possible to do this with the orthogonal layout, but you can use the hierarchic layout, for example, for this. So the hierarchic layout is also often a very good choice for orthogonal layouts. It places the nodes in layers and then connects the nodes using orthogonal edges and minimizes also the number of crossings, for example. And often you can use this hierarchic layout also to use such features like partition grid or port constraints. And yeah, there's also a small question. I think this is the last one. Namely, is there the possibility to influence the number of bands on crossings? And here the answer is yes, they can be. You can control this a bit, namely by changing the penalties for crossings and bands. So basically, there is the property in the layout that you can set, or the costs that you can set for bands and for crossings. Here's also another question I see. Yeah, so the question is whether the layout algorithm also takes the node size into consideration. And yes, so in the examples, all the nodes had the same size. But we always develop our layout algorithms that they also work for any different type of sizes, so that you don't need to take care about this too much. So here it's often important, of course, that you have not too large different sizes for the nodes, because then often the layout or the visualization may look imbalanced, but the layout algorithms basically support this, and having different sizes is no problem. And then there's also the fifth question: do you have a way to compare one layout to another? For example, can I get a score or matrix for an orthogonal layout and compare it to the organic layout with the same graph? So we actually have no metrics to compare them. So there it would be also, of course, the question: what do we want to compare? Of course, you could use different metrics, simple metrics like the drawing area or the number of bands, number of crossings. But this is basically just counting. I assume that you would like to have more complex metrics. I think that we don't have very complex metrics in this, but in assessing the layouts or in comparing the layouts. But it's also very difficult, I think, to compare an orthogonal layout with an organic layout, because they basically are really different styles of how to lay out these. There's still some typing in the chat. I'm shortly waiting. Okay, some colleague of mine also says that there's no predefined metrics for the layout. The API itself would also allow you to calculate metrics, for example, to compare the number of bands, the aspect ratio, and the white space ratio. Of course, this is what you always can do, so such simple metrics. And I think with this, all questions are answered. If you still have some questions, then just let us know. So for example, write us an email or put the question below the YouTube video, and we will try to answer them as soon as possible. Yeah, and with this, I would like to wrap up the webinar, and I thank you for attending this webinar, and I wish you happy diagramming.